So we remember this particular slide where we have a model image in this segment. This was the UV coverage, and this was the antenna layout. So it went from 2 to 256, and you finally have an image coverage then. So we did more than that, as there were more things were covered. So let us jump to some basic things. Yeah. So yeah. So basically, ultimately, what happens is that you have we have talked about that you have the visibility. Okay. So visibility. So yeah. So basically, let me just go ahead with this. So visibility is just nothing but the Fourier transform of the eye, the image in the sky. So supposedly there was, and we have done uploaded a small tutorial, a small demo where we have shown how the analysis is done actually in some software called CASA, CASA, Common Astronomy Applications. Okay, so CASA or CASA has done all the analysis, and it's been also made into a small demo, which is already uploaded or will be uploaded. I'm not sure exactly what is the status, but it will be done. So the most important part is that the visibility is a Fourier transform of the eye. Now, supposedly, you have now supposedly you have discrete coverage in the U and V space, because you have finite number of baselines, and so your UK and VK are finite numbers, and so that's causes the major problem. So, sorry, I'm having a technical challenge there. Yeah, fine. So visibility as a function of U and V, just simply put a transform of I, which is over here, the I. Now, because of finite number of baselines, why finite number of baselines? We have, supposedly we have an array of in a Y shape, right? And we do have very fixed pairs of X, I, and J, right? So that only causes some U, K, and VK to be covered in the U and V space. So we can write this in terms of the sampling function, which we already mentioned last time, which is nothing but a bunch of delta functions, this time Kronecker delta, where you have the sampling equal to 1 when there is a response, and it is 0 when it's not. So we have already said that this multiplication of the V, the visibility, with the sampling function is Fourier transformed to this I, which is I dirty, or the corrupted mean, basically. That way what we done. So that part was also involved when we were doing image. Now, imagine one thing. This is the Fourier transform. Now, we already know that there is something called a fast Fourier transform. And this, in order to make it happen, because this simple FT is a discrete Fourier transform, it takes a long time to operate. To save time, to make it faster, more economical in computation, we use fast Fourier transform. But this requires the data to be gridded. It has to be a regular gridded data, not just arbitrary. So we have to first grid the visibilities, which is a function of U and V. That has to be gridded, and then it Fourier transforms into the grid of the image. Okay, in this case, the image that also turns out to be another image. This we did little bit when we were discussing one of the problems which came out, because if this has nx times ny number of pixels, then this also will be having nx times ny number of pixels. Okay, typically nx and ny are equal, so you have the regular grid, a square grid instead of a rectangular grid. So typically you have nx for all major purposes is equal to ny. And this also has some kind of a value of 2 to the power n, okay, to make the Fourier transform work properly. Okay, so that's what was here. Okay, the next slide. Okay, start here. Okay. Yeah. So what happens is then, ignore that. Fine. Yeah. So yeah. So now we have the visibility and the sampling function. And now, because of we have to grid the data, we also have a gridding function. Now, don't worry about all this thing. We are just discussing just to complete the picture. None of this has any relevance to the exam, end exam. Don't worry about it. Just try to enjoy what we are learning about that. So, effectively, am I audible still?
Yes, sir.
Oh, I can see you. Yeah. So we already said that the visibility and the sampling function are the multiplicator. And now, because of gridding, because of we have to grid the data, this is something like a gridding convolution function. So we use this function as gridding convolution function. Okay. And that finally gives rise to our I, which is uh, the dirty image. Okay, so next. Right. That's one of the thing, and will come to the fact that how we finally get rid of that statically component. But before we go there, one more interesting thing to do is that we discussed this earlier, that the visibility which we observe is not ideal. So we were discussing so far, assuming that this is ideal. Okay, there is no corruption, but we know we are observing this with the sky, which has two antenna. Each antennas have a lot of electronic components, an LNA, a mixer, etc., etc. So all of them has some kind of a gain attached to it. Because remember, we have these problems we did multiple times. What happens if you have a cascading amplifier? There's three stages. Each stage has its own gain and own noise temperature. So there will be some gains coming from the electronics part. So all those we have somehow compressed and coincised them into this particular expression, which all defines the non-ideality of each telescope or pair of telescopes. How do we go about that? First of all, I is the ith antenna and J is the jth antenna. So any two pair of antennas. GI and GI is the individual antenna gain as a function of time, and frequency will also be there. GJ is for the next antenna in the pair. GJ star comprises of the complex conjugate. So the star here is the complex conjugate. How do we define complex conjugate? Suppose you have a complex number, Z is X plus I, Y. So Z plus Z's conjugate is X minus I, Y. Okay. You can also represent it in terms of e to the power R e to the power I theta. It's equal to R e to the power minus I theta. Okay. So let us stick to this, come back to here. So GI and GJ are the two independent antenna dependent gains. Each gain is dependent on just that particular antenna. Then there is something which depends on the baseline or the pair of antenna, cannot be factored individually to this antenna or this antenna. It depends on the baseline. There are numerous other things. Let's not worry about it currently. And there are two other things. There's an additive offset and simply thermal noise. Okay. So remember, this is the ideal visibility which we have been using so far in the previous slide. Now, this is the real observed one. Okay, and you have to actually get rid of all of this to get to the ideal visibility, because that's what we actually are interested in. You're not interested in a non-ideal situation. You will take care of that by the process called calibration. So when we are using this term in the demo, please refer to this particular slide. This is called calibration, which takes our non-ideal visibility of VI, B tilde IJ observe, goes as close as possible to the VIJ, often says ideal or model, and this process is called calibration. Okay, that's all. Okay, another thing to know is that there is something called a thermal noise, which comes again the similar thing, like you have a system temperature, and you have that causes the basic perturbation in the signal detection. But as you take more and more number of samples, if this term is following zero mean version, then it reduces to zero. Okay. Ideal after we samples. Okay. So that's one of it. I skipped this part. Yeah. Another important thing which comes into this discussion is that something called there is a redundancy in the entire observation. Like you have three pairs of antenna, uh, I, J, and K. Okay. So, so, so yeah. So I, J, and K, three antennas. And so if you write down the expression of the non-ideal observations clearly, you can see if you have three pairs of antennas, sorry, three antennas, and if you write down all the phases correctly, so you have a GI, GJ star, then GJ, GK star, and then GK, GI star. So if you write down all of them, then this phase is essentially gets cancelled out, and this is called the closure phase. If there is no systematic part in it, they will basically cancel out. Just don't worry about it right now. Just remember this is a very interesting property by which a lot of other effects which cannot be taken care of by simple calibration can also be ensured by this. One property is the closure phase, where you have at least three antenna in the loop, and for amplitudes you need to have four by the same logic. Okay, and you have I, J, K, and L in that case to make this happen. Okay? These are just simply something which we use. None of this will come in the exam, so don't worry too much about this. It's just for the fun to know. Now, another thing which you have seen is if you have uncalibrated data, you typically will see the amplitude distribution as a function of UV distance. As like this, it is more or less scattered. There you are showing 3 points from 3 different observations. One of them is a kind of what is called a flux calibrator. Another one is called phase calibrator, and the main target source. So this is before calibration. After calibration, it simply looks like in a band. And why that is so, we'll come to know very, very soon. Yeah. So you remember that we did a Fourier transform, right? So supposedly there was a Fourier transform of a source which is just centrally picked. Okay, the Fourier transform of that went to being a constant, right? So a delta function, Fourier transform into a constant. We go back to the slides of Fourier transform. You will remember in the very first few weeks, I think we have done it. So what happens is, this is that the relationship which we'll be using right now. So typically, calibrators are very compact sources. They are not resolved. So typically, the response in the Fourier space will be kind of a single line. In this case, because of their multiple frequencies, we don't really expect a line, but we expect like something like a band, which it does. Perfectly, it does for this particular case. Okay. Same thing for a point source or a compact source, the response should be like a line. For an extended source, it should be like a Gaussian, right? So it's also something like similar. It is falling as like more or less like exponential. It's a similar thing also exists. We have done the two-dimensional Fourier transform part where you can see this. So why, the question was that why do we observe these two particular things? If you go back, if you see that the visibility which is coming out of the interferometer is proportional to the Fourier transform, right? Now, when you do a Fourier transform, the entire units, everything goes for a toss. So what we do here, we observe just the correlation, which doesn't have any physical unit, because it is some correlation of the electric field strength or the voltage from the ith antenna and the jth antenna star measured over some integrated time. So it doesn't have a physical unit. So what we do, we observe a known source, in this case, something called the 3C286. It's the one of the sources in the third Cambridge survey, one of the very first surveys done. Okay, we remember we showed you the Cambridge interferometer. It's one of the first few surveys done by that. It's a very well-known source, very compact and very bright. It has to be. And we know what the values are. So we kind of bootstrap. We observe this and we know the flux, what it should be, and we know the correlation, what it have given. So if Y Jansky is linked to some X correlation, then we can find the correlation of the target source and fix a Jansky scale to it. And by doing this flux calibration, we actually impart the flux value to the data of the target field. Okay. Phase have something similar. It basically takes care of the atmospheric effect and reduces the error in the final analysis, which may be caused due to the atmospheric effects. Okay, so that's so far so good. See what next. Okay. Yeah, so this is something like what a uncalibrated point source looks like. When you calibrate it, it looks like a dot at the center. And for a target source, when it is uncalibrated, it looks like this. But when you calibrate it, it looks like kind of a big super style. That's the thing. This is taken from some NRA synthesis workshop. It's shown very well. I'm sure that the demo which we have created that shows data analysis from a GMRT data, and I hope you will go through it and try to enjoy it as well. Now, one thing which has to be shown is this is the PSF or the point spread function, which is because of one of the interferometer. This is the UV coverage. We've already mentioned this. Now, by doing the imaging, we have a 30 image. So it has the imprint of this missing coverage of the UV in the UV plane, because we don't have all possible responses in the UV plane. There is a different holes or gaps, which causes this point spread function. Now, then the journey from the point spread function produced image, which is called the dirty image, into the actual image is what is called deconvolution, because the linear path that will convolve the actual source in the sky with the point spread function, you get this dirty image. Okay, so because this front route is convolution, the backward route is called deconvolution. Okay, so I can just write down. And that's not a linear process. So there is a lot of clicks. So if you want to go this way, it's called convolution. We have already done this. But if you want to go from this dirty image back to the clean image, this is called deconvolution. And this is not a linear process and it has to be done in an iterative way. But this process is known as, again, by this particular thing, it's called clean. The most famous algorithm is designed to do this particular operation of deconvolution. It's called clean. There are varieties of many variations of this clean algorithm available and utilized as the as the interferometers gets more complicated, sophisticated, you need to develop variants of this particular algorithm to stay, concurrent with the current flow. Okay. Some other different kind of thing, like I think we have gone through the self-calibration. So the original calibration, the uncalibrated value into galaxy looks like this. If we do self-calibration and few other steps, which we have shown you in that particular analysis tutorial, you will see a very clean. Okay, so I think we will stop here for the time being. So, and really, it's almost close to 2 hours. So yeah, thanks for joining us, and really this has been a very interesting